Let's do a quick recap of the different graphs we've seen so far in this unit. Here we have a position time graph. So position on the y-axis. This is the same as a displacement time graph. So here we see 3 times where our object was at the origin, and also times where the object was stationary. We see 2 straight lines segments in this graph. Here, a positive gradient. This represents a constant positive velocity, so away from the origin in the positive direction. Here we see a constant negative gradient, representing motion towards the origin and then away from the origin in the negative direction. So notice here there is no velocity change during this time. It's just that the object starts moving, say, to the left here, and then travels back through the origin, continues travelling left onto the other side. Then we see a curved section here. When we see a curved section in a position time or a displacement time graph, that's when we have acceleration. So here we see the object is getting faster. If we look at small time periods and look at their change in position, later on over the same time period, their change in position is bigger, showing us that we have acceleration. We can also look at the gradient here. The gradient measures the velocity, and at different points on our graph, the gradient is increasing, meaning that the object is accelerating. Now looking at a velocity time graph, we have 2 things we need to remember here. 1, the slope is a measure of the acceleration of the object, and 2, the area underneath the curve is a measure of displacement. So here I see 3 sections where the object is not accelerating, meaning that the velocity of the object is constant in these 2 sections. Moreover here, I can say that the object is stationary here because we're on the value 0. So there's 3 sections here where we have constant acceleration. Here the acceleration is away in the positive direction. Here the acceleration is in the negative direction. Notice here that there's no change in acceleration as we cross the time axis here. What is occurring is the object was initially travelling in the positive direction, it accelerated and momentarily came to rest, continued accelerating and travelling in the opposite direction, the negative direction. This is what happens when you throw an object up. It always accelerates at g, 9.81 meters per second, and it will be travelling up, then on the way back down, and the acceleration hasn't changed. Finally, we see another section of positive acceleration. Here the object is slowing down in the negative direction. Now we'll have a look at the area underneath the curve. Without a calculation, the object leaves the origin, say. Let's say at time t equals 0, it was at its starting point. Does the object return to its starting point here in this motion? So, if it does return to its starting point, well, during all of these times here, it's true that our object is moving away in the positive direction. The area underneath the curve here represents a change in displacement in the positive direction. The area underneath the curve represents a displacement in the negative direction. So here by eye, I can tell that the displacement in the positive direction is bigger than the displacement in the negative direction, meaning that our object must have moved out in the positive direction away from the origin and then come back towards the origin, but still ended up in the positive direction overall for this motion. So again, it's a really good idea to be able to picture this motion. So here the object is accelerating and slowing down, coming back and then stopping. So if you can picture the motion and think of simple ideas of when is it moving away in the positive direction, it can really help answer questions here because it's very easy to get confused. Last of all, we have acceleration time graphs. Here we don't really look at the slope. The slope tells us the rate of change of acceleration, which isn't a quantity we're interested in this year. However, the area underneath the curve or the graph is important because that represents a change in velocity. First of all, we can see two sections where we have constant velocity. We're only going to have constant velocity when the acceleration is 0. Next, we have two regions where we have constant acceleration. Here the acceleration is in the positive direction, and down here the acceleration is in the negative direction. Again, the area of the graph represents a change in velocity. So this part of the graph represents a change in velocity in the positive direction. And here we see a change in velocity in the negative direction. Note that we can't determine the velocity of the object at this time when this acceleration ends because this graph doesn't contain the information of the initial velocity, the velocity of the object at time t equals 0. In a lot of situations we'll look at, the initial velocity will be 0, so we can use this area to figure out the velocity of the object at this time here. However, you could imagine that the object could have had a positive velocity already, in which case this would represent the object getting even faster in the positive direction. However, it is possible that the object could have been travelling in the negative direction at time t equals 0, and this would actually represent perhaps a slowing down of the object. Last of all, we see a section that is curved. Here the acceleration is decreasing to 0. This is similar to what happens in a car perhaps, when you hit the brakes, stopping at the lights, and then easing off at the brakes, coming to a gentle stop. However, we won't do any direct analysis of acceleration time graphs when the line is curved. One further point to note here is I've dashed off the vertical lines. In reality, it's not possible to go from acceleration of 0 and then in no time at all hit an acceleration. However, we're going to assume that the time period over which the change occurs is so small that it's not relevant in our calculations. So dotted lines here, not a solid line. It just makes the physics a little bit simpler. With graphing motion, it is an important skill, given one graph of the motion, to be able to produce the other two. So here I'm going to do an example where we're given a velocity time graph and we're going to look at creating a displacement time and acceleration time. To make the video a little bit quicker, I haven't included values here, but I'll talk about what to do if you are given the values. First, let's break it up into the time segments. The first segment here, we see a constant rate of change of velocity. This represents a constant acceleration in the positive direction. If we were given values here, you'd have to make a calculation of the gradient in this section. For the next section, the velocity is constant, representing no acceleration. In the next section, again we see a constant acceleration as the gradient is constant in this section and it's negative. I also see that the line here is steeper than the first section. So if this was just a sketch, it would be important that you'd show this as being at a greater value, or if you're making a calculation, you'd know exactly what that was. Then again, we have no acceleration, followed by a positive acceleration. A nice link here is to notice that over this time period shown, there is no change in velocity of the object. That means the area underneath the acceleration time graph should equal 0, or these two areas equals the area underneath the curve. Next, let's create the displacement time graph from the velocity time graph. So remember, it's the area underneath the curve that represents the displacement. So in this section here, the area here represents the displacement. Notice in the next time period, if these are equal chunks, this displacement would be twice as big as this one. So again, if we had values on this graph, we'd be able to calculate exactly where the displacement would be at this time, and the same for this time here. Be able to make the calculation and calculate its displacement. What's important is the shape of the graph joining these points. Here we see constant velocity. When we have constant velocity, we have a constant rate of change of displacement, so we see a straight line. However, when we have acceleration, we don't see a straight line in our displacement time graph. We see a curve. Here, as the velocity is increasing, the greatest displacement in this time section will occur for the later times, meaning we'll see a sharp increase here. So this is pretty good. However, ideally here, the slope in this section, giving us this velocity, should be matched by my curve. So this is a little bit too steep, but not bad. So we're seeing in our displacement time graph a period of acceleration. Here the velocity is increasing. Here we see a period of constant velocity as shown by the straight line here. Next we're going to see another period of acceleration, so another curved segment. What we'll find in this time is that the displacement will increase up until this point, and then it will decrease a little bit. So here I see the increase in the displacement up until this time here. Then it's travelling backwards in this small section of time, so the displacement has decreased. And because this is acceleration, I'll see a curve through these points. So when you're making these sketches, how precise the curve is doesn't really matter. It's, do you get the shape of the curve correct? Is it upwards as expected here, and then like a negative quadratic here? In the next time section we have constant velocity in the negative direction. That means in the displacement time graph I'll see a straight line sloping downwards. If you're making a calculation here, you'd check at this period, does it get back to the origin here? What's its overall displacement by adding this area to this one? By eye here, it looks like it hasn't returned to the origin yet. Let's assume for simplicity that it does indeed reach the origin at the end of the graph shown. Now we need to figure out how do we join these 2 points here. Clearly it's not a straight line because we do not have constant velocity. It's going to be acceleration. So here what we have to decide on is the curve like that, or is the curve like that? Okay, so initially it's travelling at its fastest, so the displacement will change quickest initially and then not much towards the end, giving us this curve here. So quickly recapping here, given a velocity time graph, calculations of the gradients gives you the acceleration time graph. Calculations of the area underneath the curve gives you the displacement at different times. Then you need to consider what kind of line joins the different calculated displacements. Is it a straight line or is it a curve? You will also get problems perhaps where you're given the displacement time graph and you have to produce a velocity time. I'll let you have a go at one of those yourself.